Hey everybody, it's that time of day, time to do linear algebra with me. Today we're going to be talking about eigenvectors and eigenvalues. So in general, you haven't noticed like a special relationship between A times some vector. In general, there is not a special relationship between A and the vector we multiply it with. To illustrate, let's go through a couple of examples. We've got this matrix A, and we're going to multiply it times the vector 1, 0. And if we do that, we get 2, negative 2. And then let's try multiplying it against 1, negative 1. And if we do that, we're going to get a 4 and a negative 4. And then if we do 2, 1, we will get 6, negative 2. Like, nothing really kind of ties these together. But fun fact, if we look here at the second one, we can factor out a 4 and we get 1, negative 1. Like, yes, we could factor out 2 and get 1, negative 1 there. But what makes this one special is that's what we multiplied it with to begin with. So we kind of got the same vector back. In fact, you saw this happen on your worksheet. It was the second worksheet that you ever had in this class, and so I don't really expect you to remember. But you were given this matrix, and you multiplied it with this vector. And when I had you multiply the same vector times the number 4, or negative 4, you got the same exact result. Scalar times a vector and matrix times a vector gave the same result. This is cool. This is special. So the big idea today is finding which vectors let A act like a scalar. By which I mean it has this special relationship where you get the original vector back times a scalar. So we have a special name for these special vectors. Given a square matrix A, an eigenvector is non-zero vector such that we get AX or A times V equals lambda times V, where lambda is a scalar, so it's just a number. We use the notation lambda because it is also special. We call lambda an eigenvalue of A, and then we would say that V is the eigenvector associated with lambda. Okay, so this is a special phenomena, and we are interested. Note, real quick, V equals 0 is not an eigenvector by convention, because then like every number would be an eigenvalue, and that's too many eigenvalues for one eigenvector. So let's start easy. We have a matrix. Let's check if V or W are eigenvectors for A. And if yes, what are the eigenvalues going to be? So here's A times V. That's going to be 2, negative 1, negative 1, 2 times 1, 1. And that gives us 1, 1. Excellent. So that would be like having a constant of 1 out in the front. So we would say our eigenvalue is 1. Let's check W. So AW, 2, negative 1, negative 1, 2. And then we're going to do 1, 2. And that's going to be 0, 3. So it's pretty easy to see that no matter what number you multiply this result by, you're not going to get the vector 1, 2 back. So not an evec. Okay. So checking if a vector is an eigenvector, not so bad, but like, how do we find them to begin with? Let's go with this example. This time I'm going to tell you that we have an eigenvalue, or I'm going to ask if it's an eigenvalue. And then if it is an eigenvalue, I'm going to ask you to find the corresponding eigenvector. So hopefully having an eigenvalue will tell us how to get an eigenvector. Let's chase this through. If lambda is indeed an eigenvector, we need this to be true. Or if 3 is an eigenvalue. I think I said eigenvector and I apologize. And we need it to be true for some v that is not 0. That would be the same thing as having this equals 0. V is not 0 because v equals 0 is not an eigenvector. And then what I would like to do is I would like to factor the v out, but you can't do a minus 3 because a is a matrix and 3 is not. So I'm going to get clever. I'm going to say, well, the identity matrix times v is just v still. You know, look, that right there, that's a matrix, so now I can factor v out. So a minus 3i, like that, where v is not 0. So what I want to do is I want to find a non-trivial solution to my homogeneous system. This is my homogeneous system. We're looking for non-trivial solutions because v is not 0. Okay, well, we can do this. Let's calculate out what a minus 3i is real fast. So that's going to be a minus, and then 3 times the identity matrix is this. And that'll give us -1 in all of our entries. Cool. All right, so I said I was trying to solve a homogeneous system and look for a non-trivial solution. So all we have to do is make this an augmented matrix. So here we go. Make it an augmented matrix and solve it. Well, that's very, very easy. So row 2 changed. It is now all zeros. And we have a independent variable, or a free variable, not independent, sorry. I just keep saying the wrong thing. Okay. My mouth is always like 5 steps behind my brain. Okay. So this second column had no pivot, which means v2 is our free variable. So we can say negative v1 minus v2 equals 0. We can express v1, which is our basic variable, in terms of v2. So then our eigenvector, which would be v1, v2, would be equal to this, and then we can factor out the v2, leaving us with this. Cool, so we have a lot of choices for our eigenvector. Basically, as long as v2 doesn't equal 0, it's an eigenvector. I said that I just wanted to find an eigenvector, and in general, you're only going to want one eigenvector. So then we can say that v equals, here, I'll put this, choose, that's a lot of O's, v2 equal to 1. We like 1. So then our eigenvector is going to be -1, 1. So that is the eigenvector associated with lambda equals 3. So yes, lambda 3 ended up being an eigenvalue because we could find an eigenvector to go with it. So that's cool. Now we can find eigenvectors. What was maybe a little bit surprising was that we found so many, but we really shouldn't be that surprised by how many eigenvectors we were able to get. Our knowledge of linear systems tells us to expect infinitely many. Maybe not right off the bat, so let's explain why. So if lambda is an eigenvalue of A, then we should have AV equals lambda V, where V is non-zero, which means we do the whole subtraction and we do the I thing so that we can factor the V again, just like we did on the last slide. Okay. But again, we don't want that to be equal to 0. So we want a non-trivial solution. So want a non-trivial solution for our homogeneous system, which means we are left in the world of infinitely many solutions. Another way to think of this, so since we are looking for infinitely many solutions, remember you're looking for the set of vectors such that the matrix times V equals 0. We had a special name for this. What we are looking for is the eigenvectors. The eigenvectors for lambda, they are in the null space. They are not just in the null space, they are the null space of A minus lambda I. Of course, excluding the 0 vector. So the eigenvectors are everything in the null space except for 0 because we don't want to have 0 as an eigenvector. So definition, we've got given an eigenvalue lambda for matrix A, we say that the null space of A minus lambda I is the eigenspace of A corresponding to lambda. So again, an eigenvector for lambda is any vector in the eigenspace except for the 0 vector because eigenvectors can't be 0. So the 0 vector is still in the eigenspace, otherwise it wouldn't be a subspace, but the eigenvector itself can't come from that 0. Okay, let's take this for a run. We want to find the eigenspace for A, and we want to find the eigenspaces corresponding to lambda equals 1 and lambda equals 3. So we just did lambda equals 3. So we're going to start there. So has the evec V equals -1, 1 from example 3. So then the eigenspace is equal to the span of just -1, 1. Because remember, we had multiplied that times V2, right? We had V2 multiplied on the outside, and then we just picked V2 to be 1. So any linear combination of -1, 1 is going to be the eigenspace for A associated with lambda 3. So we're going to do lambda equals 1 next. And then we know which, we don't have to repeat the find the eigenvector process because we also know this one. We have already seen today that it has the eigenvector 1, 1. That was example 2. So then we can say that the eigenspace is equal to the span of 1, 1. There you go. Those are both eigenspaces for lambda 1 and lambda 3. All right, let's try running through all of this with a matrix that we haven't seen today so that we have to put in the work. So example 5, getting big. We're going for a 3 by 3 matrix now. We've got A is this 4, 2, 3, blah, blah, blah. If lambda is equal to 3, if it's one of our eigenvalues, let's find the basis for the eigenspace of A. Okay, so that means we need to try and find eigenvectors because whatever generates the eigenvectors generates that eigenspace. So we can do A minus lambda times I, where lambda is a 3. So that matrix is going to be, so you just go through and you subtract 3 from the diagonal. I'm being lazy. And by the way, if my laziness is ever so lazy that it causes understanding problems for you, please tell me. That way I can slow these videos down. But I think we're at a place where I can do that subtraction quickly. Okay. So now to find the eigenvector, remember we're trying to solve this guy. So to find the eigenvector, I need to make this a homogeneous system. So here's our augmented matrix. There we go. Augmented matrix. So now let's take out row 2 just by adding row 1. So 1, 2, 3, 0. And that canceled out perfectly. And then row 3, I'm going to take that with 2 times row 1. And that also cancels out completely. So then V2 and V3 are free. So that means we're going to say that V1 equals negative 2 V2 minus 3 V3. Sounds good. So then our eigenvector can be described as negative 2 V2 minus 3 V3, V2, V3. And then we can split this up. Negative 2, 1, 0. Negative 3, 0, 1. Okay. So then the basis for the eigenspace of A corresponding to lambda equals 3, because this stuff, we only got this stuff because we plugged in the minus 3 for lambda up here. So then the basis is equal to just those 2 vectors that we've got. And then I would just like to point out, just for clarification, that we are normally interested in one eigenvector. So over here, an eigenvector for lambda equals 3 is, and we can say v2 equals v3 equals 1. Just set them both equal to 1. And then v would be equal to negative 5, 1, 1. So that would be an eigenvector. You could have picked them to both be negative 1. Or by both, I mean v2 and v3. You could have picked 1 to be 1 and 1 to be negative 1. You could pick 1 to be 0 and 1 not to be 0. A lot of different eigenvectors. Anything in the span of these two vectors. Okay. I think I've beat that horse to death. So key results. Key results for eigenvalues and eigenvectors. Let's think about if lambda equals 0 is an eigenvalue for A. Remember, I said that we couldn't have an eigenvector that was 0, but that was eigenvectors. That wasn't eigenvalues. We might still have eigenvalues that are 0. That is an okay thing. So what would happen? So then we would have, then there is a non-zero vector, so v that doesn't equal 0, such that, and here's our definition, we've got AV equals lambda v, but if lambda is 0, that's just the 0 vector. So then that means since v is non-zero, but we are still getting, this is our homogeneous system. So then the homogeneous system AV equals 0 has a non-trivial solution. And then we know things about that because we have IMT. That means A is not invertible because we proved everything in IMT was equivalent. And if we have that, if we have non-trivial solutions to our homogeneous system, we get A is not invertible. So that means we have more food for our IMT monster, basically. Here we go. Theorem, IMT continued. A is invertible if and only if 0 is not an eigenvalue of A. So we can just add this statement of 0 is not an eigenvalue of A to our IMT. And that'll be reflected in the PDF that I've got on Sakai with IMT stuff sitting in it. Okay, so that's cool. It gives us the next theorem, sort of. Remember, we've got lots of like linear independence things that come with IMT. So we're not going to directly get this next theorem from IMT, but it is a consequence of that. So we've got lambda 1 through lambda r. They are distinct eigenvalues of the matrix A. We've got their associated eigenvectors. If these guys are distinct, which means you don't have lambda 1 equals 1 and lambda 2 equals 1, no doubling up. Their corresponding eigenvectors are linearly independent. So why is that true? It's not immediately obvious. We're going to start with suppose there is a linearly dependent vector in our V1 to VR. We're going to call him VP plus 1. So why I'm doing that is it doesn't matter what order our vectors are in. And so I'm just going to say, let's say that our problem vector is VP plus 1, and then he depends on all the vectors in front of him. So we're going to say depends on V1 to VP. So then all I've done is say, let's just specifically order our vectors like this, because it makes my life easier and notation easier. Could VP plus 1, could this P plus 1 be R? Sure. Nothing I've done prevents him from being R. And it's simply because it doesn't matter what order we put our vectors in when we make this list of vectors. So we have this guy depends on everybody in front of him. So that means that he is a linear combination. That's what I meant by it makes my notation easier. So here we go. What I'm going to do is I'm going to multiply my star equation by A. And that means I have C1 A V1 plus all the way up to CP A VP A VP plus 1. But these are all eigenvectors. That means like AV1 equals lambda 1 V1. And same goes for everybody else, because they were all eigenvectors. Okay. What I'm also going to do is I'm also going to multiply that star equation by lambda p plus 1. And that's going to give me a different equation. That's going to give me C1 lambda p plus 1. Oops. V1 VP lambda p plus 1. No. There we go. And I'm going to call this equation smiley face, and this is equation heart. So what's going to happen is I'm going to say, let's take the heart equation and subtract the smiley face equation from it. So that means we would have this term minus that term. So that's going to be C1 and then lambda 1 minus lambda p plus 1, V1. And then we're going to go all the way down the line, CP, lambda p minus lambda p plus 1. And then we have, on the right-hand side, we have that term minus that term. Those are exactly the same. And so we get the 0 vector. But I said all of the eigenvalues were distinct. That means this guy, not 0. This guy, not 0. The only way to get 0 is going to be C1 equal to CP equal to 0. Because these guys are linearly independent. It was VP plus 1 that was the problem. Everybody else was fine. So then, I'm going to make this smaller. So then, if all of our coefficients of C are equal to 0, let's plug that in to star. So star is this guy again, right here. That means you have 0 plus 0 plus 0 plus 0 is equal to this guy. So that means our problem vector V was equal to the 0 vector. But I said he was an eigenvector. But eigenvectors can't exist. Or can't be 0. So VP plus 1 can't exist. And by that, I mean there is no linearly dependent vector VP at plus 1. So if there is no linearly dependent vector, that means they're all linearly independent. Okay. You're like, okay, Gracie, that was a nice detour. So we were looking for eigenvectors, and I found out that I could use eigenvalues to find them. What I would really like to know is, how do we find eigenvalues? Thank you for that, but how can I find eigenvalues so that I can move on with things that I really care about? Well, let's go over a special case. Let's go over triangular matrices. So if A is triangular, then the eigenvalues are just the entries on the main diagonal. And this is less tedious to show. So we're going to go over this. And if the last one didn't make sense, it's okay. I was just trying to show that we're not pulling things out of nowhere. But this one, this is something that I would definitely expect you guys to understand. Okay, so proof. We're going to say that A is triangular. Specifically, I'm going to go after upper triangular, but for no real good reason. Lower triangular has pretty much exactly the same proof, and so I'm just doing the upper triangular case. So then if it is triangular, we have A minus lambda I would look like this. You just take the diagonal, you subtract off lambda, and then up here is a bunch of entries we don't know, but the bottom part is all zeros. Remember, that's triangle, is you got zeros on the bottom. Okay, what's cool about this is we've got echelon form. So now what I'm going to remind you of is that we're going to have solutions if we have free variables, right? Because remember, we need the infinitely many, we're in the infinitely many case. So we need infinitely many solutions. So we have non-trivial solutions to A minus lambda I, V equals 0. Okay, we did discuss this earlier. Okay, so that means we need free variables. We can get free variables if we have a column with no pivot. So, for instance, if this term right here were equal to 0, that would be a column with no pivot. If this term right here was equal to 0, that would be a column with no pivot, and so on. Anything on the diagonal, if any of those entries are 0, we're going to have a column with no pivot. So then AI minus lambda I. So if anything on the diagonal is equal to 0, we get an eigenvalue, right? So that means lambda I equals AI are our eigenvalues. So then lambda equals all the diagonal entries. There you go. So hopefully you guys did follow that one. This is a very special case, of course, for finding eigenvalues. And we're going to go into the general case next time. Right. So thank you guys for listening. See you next time.